in this video, we're going to be trying to solve this kind of problem. For the polynomials, use the LC to describe the left and right hand behavior of the graph. By the FTA, state the number of zeros of the function, and state the zeros and sketch the graph, and finally identify the intercepts. And we're going to be going over what each of these terms really means and how to solve each criteria. So first is the LCT, which stands for leading coefficient theorem. And what this theorem helps us with is it helps us identify the end behavior of the polynomials based on the leading coefficient and the degree of that polynomial. So we have here 4 cases that apply to polynomials. So one of the cases that we can see is if the leading coefficient of the polynomial is positive and the degree of the polynomial is even. In this case, the right side will go upwards and the left side will also go upwards. And this basically tells us that the y values will approach infinity as the x values approach infinity and negative infinity, which are its limits in this polynomial. And an example of this kind of case is positive x squared. Our next case is the negative leading coefficient and an even degree. And this tells us that the left and right hand sides will both go downwards and approach negative infinity. And an example of this is negative x squared. Next case we have is positive odd. So this is positive again means a positive leading coefficient. And odd this time means an odd degree of the polynomial. So that means that the polynomial has an odd degree. And in this case, the right side will go upwards and approach infinity, whereas the left side will go downwards and approach negative infinity. And an example of this is positive x cubed. And our last case is if the leading coefficient is negative and the degree of the polynomial is odd. And in this case, the right side will approach negative infinity while the right side will approach positive infinity going upwards. And an example of this is negative x cubed. So this is what your polynomials might look like. This seems kind of messy at first, but once we get to know what we're really needing to focus on for the leading coefficient theorem, it'll be a lot more clear. So as the name suggests, we're just going to be looking at the leading term only. So if we organized out a polynomial, this would just be the term with the highest degree where n is the highest. And so here we can see a sub n. This is our leading coefficient. So it is just the coefficient on this x with the highest degree. And our leading coefficient theorem sees if this is positive or negative. And our leading coefficient theorem also looks to see if n is even or odd. So as I was talking about earlier, first thing we're going to need to do is organize this out, organize each function out to go from the highest term to the lowest term. So if we organized a function like this out, we would end up with something like this, where the highest degree term is first and the lowest degree term is last, or this is our constant term. And we can see that the highest degree is 6, so this would be the degree of the polynomial, so it would be even. And the leading coefficient is -3, which means the leading coefficient is negative. So for this polynomial, it would be that the right side and left side are both pointing downwards. Next, we're going to be looking at the fundamental theorem of algebra, which states that for any polynomial, the maximum amount of roots that polynomial can have is the same as the degree of that polynomial. So we stated earlier that the degree is just the power of the highest degree term. We have examples here of the quadratic, which is a polynomial with degree 2. And it can have a maximum of 2 roots, but it can also sometimes have only 1 root or even sometimes no roots at all. So you can see that here the graph is intersecting with the x-axis at two different points, which means it has two roots. Whereas this graph, the function is only touching the x-axis at one point, which means it only has one root. And here it's not touching the x-axis at all, which means it has no roots. And we can see that shown here, we can see that the degree of this polynomial is 3 because that's the highest power. And that means that a function of degree 3 could have up to 3 roots. But obviously we can just see looking at this graph that it only has 2 roots, one here and one here. So next we're going to be looking at finding zeros, and there's many methods of doing this that hopefully you've learned before, but here we're just going to be using factorization for simplicity's sake. So we're going to take this function right here and try to find the zeros of it. So first things I'm going to do is factor this term out, and we're going to end up with something like this. Now, what a root or zero or x-intercept actually means is that it's basically the places or the points where y equals 0, or the places or points where the graph or the function is passing through the x-axis or touching the x-axis. So once I have it factored out here, what I want to do is actually turn this side of the equation to 0, because I want y to equal 0, because that's when the function will be hopefully touching the x-axis, right? So I'm going to set that to 0. And then we know that anything multiplied by 0 will be 0. So this term obviously can't be turned into 0. However, these terms with some manipulation of x can be turned into 0. For this one, if we set x to -4, then this term will be 0, and then if we multiply it out, then it will become 0. So -4 works. And here, if we plug in 3 for x, this will become 0. 0 squared is 0. 0 times the rest of this stuff is also 0. So our solutions for finding the zeros or roots are -4 and +3. Last, we're going to be looking at the intercepts. So we're going to take the same function from before, and this time we're still going to factor it out. But to find the intercept, we've already looked at where the function passes through the x-axis, but now we need to look at where the function passes through the y-axis, which is right here. And we can see at this point that our x value will be 0. The x is 0 at the y-intercept, right? So what we can just do is plug in 0 for the x value here, like so, and then we can simplify it out step by step, and we can see that here the 1/4 and the 4 cancel out nicely, just leaving the 3 squared, and that leaves us with 9. And we can see that right here, this point is 0, 9, which is our y-intercept. So now with all of this, we can try to solve some example problems. We have this function right here, which the graph is displayed here, but we're going to try and not use the graph to solve this function. So first we can see that the degree of this function is 3. And a trick to doing that is just looking at the highest degree in each of these terms that will be multiplied together, and choose the highest degree from each term and just add those together. So this, since it's just like a leading coefficient, has no degree, so we're going to ignore that. The degree of this term, the highest degree is 2, and the highest degree in this term is 1, which we can't really see there, but and if we add those together, we will get a degree of 3. And that is odd, and our leading coefficient is negative. So by the leading coefficient theorem, we can determine that this will have a negative odd behavior, which states that the right side will go downwards and the left side will go upwards. And we can see that reflected in the function graph. And next we're going to use the FTA to determine how many possible roots this function can have. And we earlier determined that the degree of this function is 3. So it is possible that this function will have up to 3 roots, but it can also have any number less. And to then actually find those roots, what we're going to do is factor this out. So with this term, we can just pull out an x to make things simpler for us. And to find the roots, I'm going to set the y to 0 again. And then we know that if any of these terms is 0, then this whole thing will become 0, which works for the outcome. And so we can, to get this term to be 0, we can just set x to 0, right? To get this term to equal 0, we can set x to -4, and to get this term to equal 0, we can set x to 3, and we can see that those are our solutions. And lastly, we are going to be looking at the y-intercept, because we've already found these x-intercepts. So the y-intercept, what we're going to do is take this factored form again, and just plug in zeros, and we'll get this number, and luckily for us, this term is already 0, and anything multiplied by 0 is 0, so this whole thing will just become 0, and we can see in the graph that's where the y-intercept is at the origin. We're going to try another practice problem, this function right here. First things first, we know that the degree is 3 because the highest degree in this term is 2, and the highest degree in this term is 1, and we add those together to get 3. And the leading coefficient is positive, so we know that the behavior here will be positive odd because 3 is odd. And yeah, that states that as the x approaches infinity, or as it goes to the right, it'll go upwards, and as it goes to the left, or negative infinity, the y will also approach negative infinity, or going downwards. And we stated earlier that the degree of the polynomial is 3, so this function, again, can have up to 3 roots, so our degree is 3. And next, to find those roots, we're going to factor out this function right here. And to find the roots, we're going to set the y to 0 again. And to get that, we need these terms to become 0. So we can set the x here to 1 to get this term to equal 0. We can set this x to -2 to get this term to equal 0. Or we could set this x to 5 to get this term to equal 0. And those are our possible solutions for zeros. And yeah, we can see that reflects nicely right here. Lastly, we're going to be looking for the y-intercept. So again, we will set the x this time for our factored out form to 0. And we will get this. So if we simplify it out, we will get this 1/2 -1 times 2 times -5, and the 2 and the half cancel out nicely, and the -1 times the -5 will just give us +5, and we can see that in the graph, the y-intercept is right here, -5, or +5. Okay, so lastly, what we can do to just double check through our problems is we can plug in values. So this is the same problem from the previous slide, right? The same function. And this is the factored out form of the function. And what we can do is we can plug in values in the ranges between the roots to check for the behavior, for the y behavior between those roots, because we already know that the y behavior at the roots, the y will just equal 0, right? But between the roots, we just want to double check our graphing and see if the range here will really result in positive y's, and the range here will really result in negative y's. So what we can do is we can plug in numbers. These are just numbers that I picked that are inside of these ranges, and basically, all we have to do is just plug in that number we picked earlier into the function and see what the output is. if the output is negative and we drew that the y values were negative in that range or that area, then we know we drew the graph correctly. And that's just a way to check to make sure that the graph is drawn correctly if what we need to do is draw a graph. And that is everything I have for these kinds of problems, for how to solve these kinds of problems for polynomials. And thank you for watching.